To Max-Q or not to Max-Q? That is the question. Whether 'tis nobler in the mind... Oh, no, wait. Max-Q, 300 watts or not? Blackwell RTX 6000. Blackwell RTX 6000. This looks a lot like a 5090, but it's shiny. Look how shiny it is. And there's some extra connectors on the side here for sync and everything else. Standard 12V power connector. This is a 600 watt card. This is RTX Pro 6000. Blackwell. So it's RTX 6000, but Blackwell. And they say it RTX Pro because they don't want you to get it mixed up with the prior generation RTX 6000, Ampere and Ada, and then there was even one before that. And then also the Max-Q edition, which looks more like a workstation card and comes in at a 300 watt power envelope instead of a 600 watt power envelope. I did a live stream the other day and we've got some fun, interesting Blackwell coverage because I'm a crazy person, and yes, this isn't from NVIDIA, this isn't seeded. I spent actual money to acquire this, about $9,500 give or take. So yeah, I've got this card and we're gonna do some stuff with it and see how it goes, because again, crazy person. This is the P&Y edition. Let's look at what you get in the box and all that sort of stuff. This is a literal box it arrives in from Vietnam. That might be important if you're interested in the tariffs situation. In the box, it comes with an NVIDIA branded NVIDIA part number 12V2 to 4 8-pin power adapters. It also comes with a mounting bracket. This will be important for OEMs because you can screw it into the end of the card and secure it in the PCIe slot. Plenty of packing, and also mounting screws to go with the aforementioned bracket. They use a T5 head, looks like. P&Y. And this is literally how that arrives. It's very similar to a 5090 in that it has 4 display ports instead of 3 DisplayPort and 1 HDMI, as with other workstation cards. The Max-Q edition is very similar to past Max-Q edition. It has a blower, fan, similar connections, also 4 DisplayPort. It's really not a lot different than other workstation cards, and that's what NVIDIA is kind of catering to and playing to here. Is this card is 600 watts. This card is 300 watts. At half the power, can you expect half the performance? But we'll talk more about the benchmarks in a second. If you were gonna rock 2 RTX Pro 6000s in a workstation, you're gonna need a special power supply. Maybe something like the Zeus 1650R. This is a 1650 watt power supply. It has 2 12V2 connections. It does require 120 volts to 240 volts in order to deliver 1650 watts. But this is the only power supply I know of that could reasonably run a Threadripper or Xeon Workstation CPU along with 2 of the RTX Pro 6000 non-Max-Q GPUs. Whereas the Max-Q, 300 watts. Basically any workstation will be able to support 2, 3, 4 of those. Now neither of these cards have NVLink or bridge or anything like that. You can kind of do bridging through the PCIe bus, but that is slower than NVLink. So something to keep in mind. Now for our testing, we're going to be using our Falcon Northwest 96-core Threadripper system with 512 gigabytes of memory. This is in a rack case, and we reviewed this previously. It is Threadripper Pro. It is awesome. It is glorious. And for our Windows testing, we'll be using our Falcon Northwest Xeon Workstations. 56 cores. It is Sapphire Rapids. It is not Sapphire Rapids Refresh. So if you have a Sapphire Rapids Refresh workstation, it's probably going to be a little faster. But my Sapphire Rapids workstation is a little overclocked, so probably somewhere in the middle. It's a pretty good little system. Heck, we'll even throw in a couple tests with an X3D gaming CPU, because why not? This Pro 6000 has a few more ROPs than a 5090. 96 gigabytes of VRAM. That's really what you're paying the price difference for here, because the street price at the time that I'm doing this, it's about $10,000, $11,000, give or take. I think MSRP was supposed to be $11,000. They were obtainable very briefly for like $8,500. This video is in no way commentary on the costs there. It's a product in a class by itself. I will tell you that I think that before this product is obsolete, we will see something akin to general artificial intelligence. Like whatever the metrics and benchmarks were for general artificial intelligence before large language models entered the scene, I think that we will have that before these cards are obsolete. So that's right around the corner. Let's also not forget that last year H100s were $40,000 on eBay. And this absolutely eats an H100's lunch for breakfast. Wait, that's not right. And this absolutely will eat an H100's lunch. Jensen said it best.
But I said before that when Blackwell starts shipping in volume, you couldn't give hoppers away.
All right, let's get to the lab and put this in the Linux machine and see where we go. So we've got our GPU set up in our Falcon Northwest rack system now. It's running Ubuntu 24.04 LTS, and the guide in the forum walks you through getting CU 128, because you're gonna need that version in order to be able to interface with Blackwell, and probably actually a newer version. And also, this is a floor on performance. Typically, NVIDIA squeezes out a little bit more performance 3 to 6 months after a GPU has actually launched. I mean, this literally availability at the time that I'm filming this just happened a couple of days ago. It's still generating. I like to use a prompt, which is, write an efficient program to search for perfect numbers, which you can get a short response to that, or you can get a really elaborate response if the model understands Mercedes primes and the great internet Mercedes prime search project, and you can go down a bunch of rabbit holes for that particular prompt. It's not a lot of words, but it'll generate a huge amount of output potentially. And sometimes, depending on the complexity of the model, it may get stuck in a loop, and it may be asking itself a lot of questions. It's a great prompt for doing benchmarks. At 600 watts, this model can run at about 19 tokens per second, and as you can see, we're 56 to 60 gigabytes of VRAM usage of our 90 gigabytes. That's going to give you plenty of VRAM for a KV cache or a bigger context window, that sort of thing. Personally, I don't really like the distilled models. Unsloth, I think, does a better job of distilling down DeepSeek into something that can run, that can fit in 96 gigs of VRAM, or 2x 96 gigs of VRAM if you're gonna do that. The performance on Linux is also better than it is on Windows. We'll cover some Windows stuff in another segment in just a little bit. But generally, this is really impressive. At the 300 watt limit, it's about 16.5 tokens per second. So it really doesn't make a significant difference in performance, 16.5 tokens per second versus roughly 19. That's an 18% performance penalty, which is right in line with our expectation of 10 to 20%, 10% being a best case scenario at 50% power usage. Now let's talk maximum achievable mapmul flops, or map finder. This is a Python script. It's great. You can run it on basically anything, even a potato class computer. Our RTX 5880s that were in here could do about 160 teraflops, give or take, each. So at about 300 watts, 160 teraflops, that's what you could expect. 300 watts on Blackwell, however, we'll see that it's quite a bit faster. You also have to let this run for a little bit. Now, this does not use a significant amount of VRAM. This is mostly just things that are running on CUDA cores. Already our peak computational capacity on this thing is 259.9 teraflops. I'll just go ahead and spoil it. When we let this run for a little while, it's about 301 teraflops, give or take, at the 300 watt power limit. At the 600 watt power limit, however, it is 386 teraflops. So again, we're roughly in that 20%-ish performance delta at 50% power utilization, which is really pretty darn good. Also, take a look at the temperatures of this card in our rack system. It's only 62 degrees C, and the fan is only running at 37%. The 96 gigabytes of memory on this card contributes significantly to the heat output. It's also possible to use NVIDIA SMI, the SMI tool, to fine-tune memory speed. And so when you run the memory slower, if your workload doesn't demand faster memory, you can put more of that power budget into the cores, because really it is a power and thermal budget. At 600 watts, your cores and your memory can basically run unconstrained, but you can still fiddle with the wattage that you send to cores or memory with NVIDIA SMI commands. So you can squeeze out a little bit more performance, and that's how we got our Blender benchmark record. Now, our 300 watt power limit, the card does have little excursions where you'll get a little bit more of a burst of workload, but our median is 288.4 teraflops, and our max is 368.2 teraflops. And generally, the larger the job that is running in our Python script here, the closer that it is going to be to the upper number, as long as it's staying within that 300 watt power envelope and it's not facing any thermal issues. And just something I want to point out, when you're at the 600 watt power limit, it doesn't mean the card is always pulling 600 watts. It still only uses what it needs, up to 600 watts. And 600 watts is a non-trivial amount of power, don't get me wrong. But this thing is running full tilt. We're at 78 degrees C with the fan at 47%, And it's teetering between 420 watts and 599 watts, 600 watts, occasionally like 602, 603 watts. Because that's all it needs to run this particular benchmark, even though we're running through the same number of iterations that we were when we were at 300 watts. So for the maximum achievable floating point operations per second that you can get from this card, at least as far as the Python script goes, it seems that you're not really power limited because the card isn't pegged at 600 watts all the time, and you're not really thermally limited as long as the card can cool itself. Depending on your setup, your chassis, and everything else, the card may limit itself thermally if it can't keep itself cool, although it is a very effective cooling solution for 2 slots, or it may be limiting itself power-wise, whereas the Max-Q version, it's not really going to be a problem because it's half the wattage. It's producing half the heat, keeping it cool, making sure that it's available power budget. Not really going to be much of an issue for the card, but it does have reduced performance as a result. If you look at our peak teraflop computation, there's really not a lot of difference between 300 watts and 600 watts. The difference comes in sustain. How is the 300 watt configuration able to sustain the computation? And that's where you can see a difference in this particular scenario of up to 28, 29%. Real world is going to be closer to the 20% figure, I think, but for this particular Python script, it can be as much as 28%, as evidenced by the output of our script here. Now, this delta between 300 watts and 600 watts got me curious, and so I decided to run our Blackwell Pro 600 watt at 450 watts. Let's just pick something that's 150 watts less and see what the performance of that looks like. And taking 150 watts off the top of the power limit got us surprisingly close to the upper bound of our 600 watt configuration, which may help if you're configuring these systems, or a lot of these systems or workstations, because managing 2 450 watt cards in a workstation is a lot easier than managing 2 600 watt cards in the workstation configuration, and you're really not giving up any performance at all in that scenario when you just need the maximum number of floating point operations per second possible. It's less relevant on the AI side of things, perhaps more relevant on the Blender side of things. So here's our Linux benchmarks results from Blender, about 5291, 2749, and 2693, and this is at a 450 watt limit. Let's try 600 watts and 300 watts and see where that stacks up. At the full 600 watts, we're at 5359, 2709, and 2688. It's a pretty decent improvement. The Blender results were really interesting from 300, 450, and 600 watts in this configuration. There wasn't nearly as much of a fall off as there was in the raw Python benchmark, but the scores for Blender were also a little bit better on Windows. So those are documented in the thread on the Level 1 forum, so you can run numbers and see the percentages for yourself. It also varies a little bit between scene, which I found interesting. If you also monitor the actual power usage of the card while the benchmark is running, it's also interesting. The card doesn't, again, 600 watts doesn't necessarily mean that the card is using 600 watts at every stage during the render benchmark. We might actually need to render something that's a little longer, a little higher resolution to get meaningful Blender numbers between the 300 and 600 watt configurations. Now, we did Windows and live streaming benchmarks on our 56 core Xeon workstation, but I thought it'd be fun to do something a little different for some more Windows benchmarks for this video. This is a small form factor machine. It's got a 600 watt GPU in it. This is the Falcon Northwest Tiki. And yeah, because they designed it so that it'll hold a Founders Edition 5090 600 watts, but nothing stops us from putting a 6000 RTX 600 watt Blackwell in here. Oh, and I've also added a 122 terabyte Solidon drive. So in addition to my internal 2 terabyte main NVMe, there's also a U.2 adapter, which is connected to our 122 terabyte Solidon enterprise drive mounted right here in the side. So yes, we have 124, 126 terabytes of online usable space for all of our AI models, 96 gigabytes of VRAM, 128 gigabytes of system RAM, and it's all in this one small little package. That's about 50 pounds of computer in a 10-pound package. Let's start with our Blender benchmark. And this is one of the best and also only scores for Blackwell RTX 6000 on the Blender database. This 16.2 something score, that's me, that's this one. That's from an earlier benchmark on this very system. Oh, and you can get a little better score on Linux. That's the Linux score, that's almost 17,000 points. Also me. Very briefly, I was at the top of the Blender benchmark database with the fastest score with just, the one GPU. I just got another score, 16,392. It's not bad. It's not as good as my Windows benchmark, but it's not bad. I'll take it. Why is Linux so much faster? My Linux score is almost 17,000 points. Time demo 1, demo Q2 demo 1. Obviously. That is 140.128. Let's run it a second time. That is 140.097. That's pretty good. That's pretty deterministic. That is at 4K 60 RTX. We'll 3D mark all the things too, because why not? 156.57. Let's also run the DirectX ray tracing test, because why not? 150.79 FPS. It can indeed run Crysis in Can It Run Crysis Mode.
I find you.
And that's Crysis Remastered in RTX mode.
What the hell happened here?
What happened indeed? Blackwell RTX 6000 is what happened. Part of the fun thing to do here is to run a gaming benchmark and then set the, so this is a 600 watts, and then change the power level of the card to 300 watts and see if it makes a difference in the gaming benchmark. So final result is 600 watts, 285 frames per second. Now we've changed the power settings to 300 watts. All right, so we got 285 frames per second at 600 watts. Let's run NVIDIA SMI and change the power limit to 300 watts. Run NVIDIA SMI again, and now our power limit is 300 watts. Let's rerun the benchmark. See what it does. 285, 190. It's a difference. This is at 4K high. Power limited to 300 watts. What about Blender? I wish it let you label the results. This is our Max-Q version, 13,445.70. Still pretty respectable. The difference between 13,000 and 16,000. It's pretty good. What about our Quake 2 RTX demo? Can we achieve 140 FPS still? 77 FPS. One more time for good measure. 80 FPS. Quake 2 RTX time demos. It's a workstation card. This doesn't matter. You just do this for the lulz. You learn something every now and then. This is one of the very, very few things I've been able to find where the numbers that I get out of the card at 50% power are close to 50%. I'm getting about 84, 85 FPS, something in that range when I run this test. And that's, it's a little more than half of our 140 FPS that we were getting at 600 watts. Most of our other tests are in that 20% performance loss category, but this particular thing is actually at about half. So kind of surprising, kind of interesting that I thought, whereas most of the other workstation style tasks, 300 to 600 watts didn't really make that big of a difference in performance. But this one thing, it does. Interesting. To Max-Q or not to Max-Q? That's a you decision, but I was very surprised. Two things in our results. One, 50% reduction in power is mostly worst case scenario, a 20% reduction in performance. That is shocking. Really, because that's almost an argument in favor of getting two Max-Q GPUs if your workload can run two GPUs, putting that in a system and not worrying about the difficulty of power. And a sub-bullet point that's surprising, that's not my other main point, is that even when we run the Pro 6000 at 450 watts, we really don't claw back a ton of the performance to go from 300 watts to 450 watts. It's very disproportionate. You got to get close to 600 watts to get the other 80-ish teraflops back from the raw teraflop compute performance. And of course, large language models suffer less between Max-Q and non-Max-Q. I mean, the performance delta is as little as 10% for half power usage when you're using large language model inferencing type workloads. I'd say average is more like 15%, but like best case scenario for NVIDIA here is on the order of 10%. It's also a very inexact science, and this might warrant a follow-up video or other future videos, or even your engagement on the forum, because AI stuff is a wild west and there's a lot of interesting things happening, and I could have totally missed something or not done something right. But let's engage in the forum, because I'm willing to work on things, I'm willing to learn things, I'm willing to run benchmarks and do other interesting stuff. So let me know, hit me up in the forum. And that kind of leads into my second point, is that I was surprised that AI and inferencing workloads were affected as much as they are, because, you know, when you look at the performance graph, the cores themselves really aren't super busy. It's mostly dependent on memory access. Everybody knows that. And when I'm running the larger models that are using 80, 85, 90 gigabytes of VRAM, I really expected that to be, you know, most of the card's power budget was going to VRAM and not a lot to compute. And that because of that, there really wouldn't be a huge performance difference in the Max-Q version versus the non-Max-Q version. But at least right now, with CU28 on PyTorch, that doesn't seem to be the case. The spread is as much as 20% on AI and large language models, although generally it tends toward the lower end of that 10 to 20% performance variance bracket between the Max-Q and the non-Max-Q versions. Because that was unsettling and a little unexpected, and if we think back to, you know, the Ada generation, the difference between the RTX 6000 Ada generation and the RTX 5880, the 5880 also had a similar 300 watt-ish power cap, and the performance delta on those for large language models was in a smaller set of error bars. So the Blackwell architecture seems to have a larger set of error bars in terms of the 300 versus 600 watts. So if you run a card at 600 watts, you really do get upwards of 20% more performance if that's your jam. But if your job can run across multiple GPUs, you may be better off configuring a system with, you know, to a workstation with 2 or 4 of these. And certainly NVIDIA is giving you options for like 4 and 8 of those in a server class workstation. Of course, a server class workstation with 8 of those GPUs, probably on the order of $250,000. And in that lens, 10K doesn't look super bad. But this is definitely a GPU no one should buy unless they earn their living with AI and inventing the next level of AI and doing the next level of stuff. It's also worth mentioning that part of the price is the NVIDIA inferencing microservices cloud stuff. There is a cloud component here that everybody has been glossing over. NVIDIA wants you to have hardware that you can develop and figure stuff out locally, but then when you're ready to build it out and scale it, they want to see you deploy the app in their cloud. They want to see you run NIMs, NVIDIA inferencing microservices. They want to see you deploy stuff to the cloud, and then that's a revenue source for them when you scale it. But while you're working on it as a developer, they give you a license. You can get that at low or no cost, depending on what it is that you're doing, just by virtue of having one of these GPUs. So that's pretty exciting. So this has been a quick look at performance, Max-Q versus not Max-Q. We've got other benchmarks and other stuff that we've been doing. Engage with us on the Level 1 forums or in the comments below, and let me know what else you'd like to see, because I've been told that NVIDIA internal is also, like, a lot of people are adding these GPUs for their internal projects, and NVIDIA is trying to get these out the door to the commercial customers as quickly as possible. But they've been showing up all over the world, not just in the US, so they should be available in your local market, but the pricing is probably a bit rocky. And Wendell, this is Level 1. If you have any questions or I missed anything or you want to engage on something, definitely hit me up. I'm signing out, and I'll see you in the forums.